Hello and good evening, everybody. Please confirm if you can hear me. Welcome to day 2 of the Bioprinting webinar series powered by Altem. Please confirm in chat if you can hear me. Good evening. Good evening, everyone. And this is such a great evening. In fact, I had a great day today, and I'm going to share some insights from my discussions with the Altem team and, of course, some people at Biotechnica. Okay. Day 2 is really exciting after looking at day 1. The kind of response we got from all of you is like incredible. I'm personally wowed by the response which I got from all of you. In fact, I would like to thank all of you from the bottom of my heart. Thank you for attending day 1 and welcome to day 2. And we are right here starting with the next session. And we have our speaker with us, and she'll be joining us shortly. Now, what really excited me after attending the first session, I would like to share with you all. You know, bioprinting in 2021, explaining someone bioprinting in 2021 is like explaining someone going to the moon in 1960s or 50s. The topic itself is so exciting and so exhilarating that I personally loved listening to Aishwarya and Team Altem. And in fact, every interaction I had in, prior to this webinar, like when we were sitting and planning all this, was so enriching, so exciting. Okay. And I want to let you know that today's session is once again going to be the same. Now, people, what would really encourage our speakers, in fact, me also, like, okay, this is my personal weakness, I would say. What really encourages us to do more, give more, and conduct more such webinars with all of you is that feeling when you guys go and share on your social media profile and say that I attended this webinar and it was marvelous. Thank you. Whatever you write over there. That really makes all of us happy at Biotechnica and in fact at Altem too. So I have a small request, very small request, just like all the time I have told you. Today, if you guys could go and share this with all your friends, bring the entire Biotechnica community together, then probably Altem and many other webinar speakers and webinar sponsors who are watching this webinar will get encouraged to conduct more such sessions, right? So it's all your good which will spread more good to all of us, right? So yes, I am eager to learn. Yes, I want you all to be eager to learn ETL, but please share, because sharing is not just caring about your own friends, but it is also caring about all the speakers who do all the hard work and come here to present to you, share with you, and all the energy which goes in the background. Like right now in the studio, there are 5 people who are coordinating all this, right? So can I have that? Can you guys share? Yes? Okay, wonderful. So with that belief that you guys are going to share, I have a small request. LinkedIn pe jao. Please go to LinkedIn, search for my profile. Just look for Shekhar Suman Biotechnica. Otherwise, our team can give the links. Okay. Tag Biotechnica fan page, Biotechnica page on LinkedIn. My personal LinkedIn, the link will be given in the chat box. And also go ahead and tag Altum. Okay. Make them know that you watched it and you loved it. Okay. If you do so at the end of this webinar, that will really encourage Aishwarya, today's speaker, and all of us to do more, give more, create more for all of you. Right? So, with these thoughts, people, I'm really thankful that all of you have come up and you all are ready to learn more. I have a small announcement to make. People who attended day one, okay, so you have filled the feedback form and now you are going to attend day two. So like this, you have to attend all the days and then only you will be eligible for the e-certificate. And trust me, this e-certificate is going to be very powerful, very futuristic, because bioprinting is the future, right? It's like how uh, automotive industry or the steam engine was to locomotives. That's the kind of revolution bioprinting and this webinar series is going to bring. Okay, so guys, are we eager to learn? I can see already a lot of ETL. Yes, we are. Fantastic. So people, presenting Aishwarya to all of you. Here we go. All right, so there we have it. Hi Aishwarya, how are you?
Yeah, hi, how are you, Shekhar? I'm good.
I'm doing great. Thanks for asking. So Aishwarya, now it's over to you. You can start the
Yes,
session.
all
Yeah.
right. Yeah. Good evening, everyone, and thank you for joining us on this session on the webinar series for bioprinting. And the topic for today is going to be soft robotics and organ on a chip. My name is, again, I'll introduce myself. My name is Aishwarya Shirur, and I'm a technical specialist here at Altum Technologies. So I'll start a little bit about us and we can proceed with the main topic. So we are a 3D innovation platform company, and we have partnered up with quite a lot of 3D solutions, say Dassault Systems for CATIA, MSC software, and then Stratasys for 3D printers, Artec 3D for 3D scanners, BioVia for life science simulations, and Selling for our 3D bioprinters. And we started about in 2011, and since then we have been, setting our foot in the industry. So, for people who did not attend the previous session, I'll just have a quick recap and tell you what 3D bioprinting is. So, 3D bioprinting is a form of additive manufacturing that uses cells and other biocompatible materials to print living structures, right? So, the idea here is to create something more layer by layer, and the intention is to mimic the behavior of natural living systems. So, 3D printing comes quite closely to, so say, tissue engineering as a technology, and the essential components if you have to print a tissue model would be cells, bioinks, culture media. And cells, we know you can use maybe iPSC cells or specific application cells, say skin cells or bone cells. So when you go a little deeper, you have keratinocytes or etc. And then in our bioinks, we have materials like alginate, collagen, hyaluron. Then there are many more examples, and obviously you know about culture media. So, just to refresh your memory, or in fact, inform a few people who just recently joined, I'll just play this video from before.
3D Bioprinting by Abir Sinyal with the Newen Lab at UNC Chapel Hill. We print things all the time. Whether they're documents, posters, or flyers, printing is an important technology in our daily lives. Relatively recently, however, printing took a big step forward with 3D printing. We could build a 3D model on the computer, send it to the printer, and we could have that object in our hands in hardly any time. What if I told you that this isn't the limit? There is more to explore. What if we could print living things made up of cells? We could make blood vessels, tissues, and organs. We could help the hundreds of thousands of people waiting on transplant lists. This idea is not too far from reality if we use 3D bioprinting. 3D bioprinting is just like normal 3D printing, except it uses living cells as ink to create living structures. Like 3D printing, you have to create a model on a computer, then layer by layer, your living structure will be printed. The first step in the process is known as pre-bioprinting. Here, the desired product is determined and studied. Oftentimes, 3D scans, such as CT scans or MRI images, are taken of the desired product and are then converted into a series of 2D images to serve as a template for the different layers. Cells are then isolated and extracted from an organism, which is often the recipient of the product, in order to create bioink. Bioink is one of the most important parts of the 3D bioprinting process. It starts with the cells that were extracted. Then, molecules called hydrogels are added to provide water for the cells. Other nutrients and chemicals are added so that the cells can grow and communicate as if they were in a living body. Once the bioink is developed, we reach the step of doing the actual printing. Using the bioink, our organ is printed layer by layer until we achieve our final product. There's not just one method of bioprinting. Different types include inkjet printing, acoustic printing, and laser printing. The most common type of bioprinting, however, is extrusion printing. This method is probably how you would normally think of 3D printing. The bioink is loaded into a printing chamber and is pushed out a round nozzle. The nozzle produces a tiny filament that is often around 400 microns in diameter, or about the thickness of 4 pieces of paper. Once you've finished the physical bioprinting portion, the final step is solidification. In general, bioink is a viscous liquid, so in order for it to become the desired product, it needs to harden. Sometimes the bioink will solidify on its own. Other times, the process of cross-linking will occur with the aid of things like exposure to UV light, physical changes like heating or cooling, or chemical changes due to the addition of certain compounds.
So, just making a quick recap, we have 3D bioprinting as a layer by layer process of printing. Then it consists of 3 processes. The first one is finding the CAD model, followed by selection of material, selection of cells. Then comes a selection of a type of printing, say maybe extrusion printing. From there, you go to the section where there's incubation, evaluation, and analysis done. So I'll start with the main topic here, leading us towards the whole idea of this webinar. So we have heard of, I think, bio-inspiration or biomimicry, right? So biomimicry is actually the way or the step where you're modeling elements of nature for the purpose of solving any sort of complex human problems. So if you talk about the examples, the example on top, which is Shinkansen, it's this popular speed train which is in Japan, and they had this when it started going about, there was a lot of problems of this sonic boom which started, and because of the problem of sonic boom, they tried to find a solution to this, where they came up with maybe a kingfisher's beak, right? So the kingfisher's beak had this advantage where it could bake through or cut through any sort of noise or any fluid. So that allowed the design of the Shinkansen. Similarly, when you now step down to the wind turbines, right? So the wind turbines are actually inspired by whales. So these are whales which have a specific type of a fin, and this fin at specific angles would allow better motion without causing any sort of energy dissipation, right? And then you have the ventilation system, and this was in Zimbabwe, where they created this inspired by a termite's den. So they took the concept of how a ventilating system of any termite would work, and they would bring that and then constructed something like a building where they could use it to allow the cooling of the entire building. Now, these bio inspirations were maybe less common that we know of. We also know of other more common examples like flights, like aeroplanes from bird. Then you have Velcro, and then you have robots. So, robots or robotics, you can say, is a interdisciplinary sector of science and engineering. And here is where you're actually collaborating a lot of things. And the goal of robotics, right? It's to design machines that can help and assist humans. So, when you talk about robotics or the type of robots, you have many types, and they have been rather distinguished on the basis of the function or how they are programmed. So, you have pre programmed types, so the ones at any machineries, right? So, these are all just programmed to do a particular job, and hence they're called pre programmed. Then you have humanoids, they are more intelligent, more realistic forms. Then you have autonomous. So they are adaptive. They are known to adapt to the conditions around them, to the changing conditions. And then you have teleoperated. So teleoperated are the ones which are operated from distance, and then augmented. Augmented robots are attached to the body, and this is supposed to be an assisting function. So, as you go from robotics, we now have a section of that which is soft robotics. So, when you talk about soft robotics, this is again a subfield of robotics, except it's not only just robotics. You're dealing with highly compliant materials like those that you find in living systems. And these are the ones which match the elastic and the rheological properties for, say, biological tissues and organs. Right? So we are coming down to the actual application in life sciences or in healthcare where this can actually come into picture. So these soft robots are actually adaptive, right? Now let's just say example of a robot. A robot is something that would have a very rigid movement. It would not have a rather fluidic or rather adaptive movement. So soft robots are supposed to be more adaptive and have the strategy of locomotion. And they're programmed in such a way that they have a specific task to take, obstacles to take care of, and adapt to any environmental conditions. So when you talk about maybe normal robots, they are supposed to be less rigid, right? Uh, when you're talking about your actual soft robots, they are supposed to be less rigid. They are supposed to be more fluidic, and they're more specialized, right? So when you see the image on the right, you see that they move so easily, quite easily, and they're mechanically compliant, and they use very versatile set of materials. And these are again found in nature, which are, say, bioinks or biomaterials. So, when you talk about soft robots, they are designed and they are supposed to help in specific functions and bring in their strengths, right? Of say example, the starfish. The starfish has a capability of bending in whatever way and still retaining its texture. So you have maybe fluids that would drive its movement, or you would have the polymer that you use itself that would drive its movement, or even maybe sensors. So, manufacturing of soft robotics, right? So, when you talk about the manufacturing, you go with these conventional methods. And when you go with them, you have maybe 3D printing or soft lithography that comes into picture. And as you use those, you have soft robots which are having a specific application, which is maybe say wearable devices or very basic, core robots, or say any exploratory robot. And then you have spin-offs of those, maybe artificial muscles or variable electronics. So they all have very, very basic functions to take care of, but then they are used in a wide range of applications, especially in the commercial applications. So that will say maybe medicine, rehabilitation, or personal robotics, entertainment and gaming, and then surveying and exploration. So when you talk about the essential parameters, right, what your soft robots need to understand, they need to be more viscoelastic. So the behavior of it should be a combination of elastic and viscous. Whenever there is a stress that is applied on that, there is a good amount of strain and it is able to recover within a specific time. So it's quite time dependent on the strain. So the next what would you say parameter would be high yield stress, that is shape fidelity. So it should be able to hold its shape right when you have done the printing. And then you have viscosity, which is the measure of the fluid's resistance to flow, which is again a very important factor while considering any material. So when you're using these materials, right, this is just a basic application or the basic parameter you would use, because these are the ones that you would start with. Obviously you will progress with time over maybe designing and modulating and maybe making changes to this, like say example making polymers that are temperature sensitive or making polymers which are light sensitive. So these modifications happen over time and obviously requires a lot of chemistry into it. So the applications, right? So since I told you these are composed of materials that match the compliance of biological matter, they're mechanically, first of all, biocompatible and they're capable of lifelike functions. So I need, say example, something to move as fast as a snake, or I want something to move as quick as a snail, right? So these are ironic, obviously, but so these examples would actually help you understand what kind of movements we are trying to generate when it comes to soft robotics. So the applications can go from say surgery. So you know about the Da Vinci, right? So this is the surgical machine which is meant to take care of the operations. While if you notice, right, every structure of it is quite rigid. So now, what if you made things more simpler? You made more softer and more elastic movements along the surgery, which reduces the kind of stress that it would put on the organ or the part of the body that your surgery is happening. So, example, diagnosis. Diagnosis would be like very simple. Then you have drug delivery. Then you have wearable assistive devices, which uses these concepts. I know robotics in general is a very vast field, but the intricacies of these, the details that you need to use in those, are related to soft robotics. Then obviously you have artificial organs and tissue mimicking active simulators for training any biomechanical studies. So these are the general applications when you talk about soft robotics, and now we'll be able to understand a better example, which will give you more understanding of the concept and why soft robotics has come into picture.
We're developing a soft wearable robotic glove that could go on a person's hand that would be useful for patients who have lost the ability to grasp objects. These could be patients with muscular dystrophy, ALS, incomplete spinal cord injury. We're trying to create a solution that will allow them to be able to perform activities of daily living. Using soft robotics, you can make a device that's a lot lighter and that is a lot easier to align and to put onto a person's hand, and ultimately we believe will also be more comfortable for the user.
For people with weak hand strength, simple tasks are everyday challenges.
Their hands most of the times are very weak and their fingers are very flaccid.
I'm not physically active at all. I can't fix things. I can't hang pictures. Just every way possible. I can't write. I drop my glasses. I drop cups and dishes and food items. And it would just be wonderful to feel like I could just control my environment a little better, my life a little better.
When we have a patient that we see, we're trying to understand what is the size of their hand and what are the motions that they're trying to perform. And then when we build the soft robotic actuators, we can actually mechanically program them by tailoring the material properties so that those actuators actually produce the desired motion that we want, that is also similar to what the motion of the fingers would be trying to do if a person was healthy.
I wouldn't attempt to pick these up with my right hand because it's just not strong enough to reliably pick anything up like that. With the glove, it's like having a hand bag that works.
The soft actuators on this device acts as an extra muscle layer, riding on the back of the finger and provides the extra force a finger needs to close around an object.
It feels really nice.
So this is just a very basic example wherein they've used a soft robot. A soft robot again is supposed to add the kind of feel of the human body, right? So like they said, the muscle layer or something. There are few other examples. You look at this octopus in the top, right? So they actually try to create a soft robot with the shape of an octopus, with the functions of an octopus. So you know how the tentacles of an octopus work. So they have this crimp-like motion and they can easily hold on to anything that's around it. So they're trying to use that as a base to create more surgically equipped devices, as well as when you have these type of artificial robots, right? So they are technically robots because actually they have sensors, they have a brain of its own, that is again the microcontrollers, and then you have other functions that are happening. So while they are just being created for the state of study, they're also allowing people to understand what is the behavior of the actual organism when they're put in that environment, when they're put in the environment with rest of the other octopus. Yes, it's quite different, but it helps in understanding the cognitive behavior. Right, this is one example which seems slightly complex, and then we go to something simpler. So when you go to something simpler, you have uh, you see that yellow and the blue and the red, right? So when you look at the yellow part and the blue, these are actually constituent of polymers, and this is a chemically modified polymer which can actually be sensitive to temperature and light, and this moves. Whenever there is a change in temperature, you bring it to light or temperature, it kind of changes its motion, it moves ahead. So that is one. And then you have this basic device. This device is just for holding on things, and this is in the manufacturing industry where it helps them pick on items of different shapes and sizes, because you see those blue parts of this, right? These are like tentacles, and they help in holding and catch hold of anything of different shape and size. So that helps a lot in packaging industries and few other sectors. And then you have a basic prosthetic. This is just an orthotic device which is supposed to be consisting of that, this polymer material on top, which stretches as your feet stretches. So it's as simple as that. And a lot of biologists now would be wondering that why are we talking about soft robotics? Where is the biology? Like, okay, yes, there is some amount of biology, but where is the cell biology aspect of this? So I will take you to something called biohybrid robotics. So this comes right after robotics, and this is quite interesting because here you have biology and synthetic components which you use. You know that whatever robots we have are actually driven by maybe batteries, maybe solar, maybe any other form of energy, right? And we also know cells. Cells have a way of uh, driving themselves. The source of energy for them is maybe the mitochondria, maybe the cells itself, the nutrition it gains, and the breaking down of certain set of food molecules. So using that idea of breaking down or making a cell active on its own is where biohybrid robotics comes in. So you reconstruct biological functions in mechanical systems, and then you obtain the biological designs you need. So I'll give you an example. This is a pill cam, and a pill cam is actually supposed to go through your entire digestive tract to take the role of endoscopy, right? So when we have those endoscopy tubes which have been put into the mouth, and then it goes to the stomach, take pictures of different sections to see if there is any sort of deformity anywhere. This pill cam when swallowed is actually painful, right? Because it's not flexible and it's not soft. So another thing is that we have so many crevices and so many turns around our system that it needs to be adaptive. We need something that can move about it more easily. So that's where you have this rather biohybrid or primitive biohybrid robot, which is consisting of a camera on top, consisting of a drug release device as well, but you'll see that there is an organism in the middle. This organism is maybe a eel or a snail, and it has this motion. It has the initial position which crimps and moves in this area, right? So although it is directed by a telecommunicating device to take the images, it is actually driven by the organism itself. And yes, this seems quite primitive, but I'll take you to something more interesting. So I'll start with this example. This is a skin ray. So actually, this is an elastomeric skin structure which is being made, within which you have your cells being embedded, and then you also have this golden skeleton which is supposed to act as a conductor of electricity, right? So this whole organism is actually a biohybrid organism, and it's quite fascinating because now this just does not move like that. It's cardiomyocytes being put, and they have genetically modified to actually be receptive to light of different wavelengths, different frequencies. And so as you continue watching this, so this artificial creature, um, I mean, this is quite fascinating to understand that you're creating an artificial creature, and somewhere it might be confusing to understand where is this application. So, as they said in the end of the video, they said that this would be used in tissue engineering because understanding the movement of your heart and the cardiomyocytes is quite essential. And while you are using that as a major understanding for a creature like this, you're also creating a sort of cognitive behavior for the rest of the animals which it interacts with, right? So after this you have your other example, which is again another fascinating example to me. Hold on. Yeah, so this is actually a skeletal muscle. They have taken a skeletal tissue that they have cultured, right? Once they have cultured it, they have attached this and they have tested it at different speeds. So there is an electrical stimulation given on the top, which obviously stimulates your muscle. As the muscle moves up and down, you have the rest of this entire device moving. So obviously this consists of sensors to understand the speed, to understand the pressure it's taking, and they would use this to understand few other motions. For example, picking something. You are trying to make a miniature model of your muscles. Basically, this is what it's trying to do. It's acting like a small finger. So it moves along the ring and it's dropped accordingly. So it has some amount of strength to lift something as heavy as that chip that they have created. So this was the example, and trying to understand how this actually comes into picture when it comes to bioprinting, right? This is where we have our extrusion based printers which will do the job for you. So as you watch this, you will be able to get some more clarity. So you need to select a model. For example, the model of a stingray or a year in this case, but we would take say a stingray, right? We would select what device, what dish we want to print it on. Pressure temperature controls, as I said, materials that you're going to use is also something integral, followed by photo curing if necessary. So while you do this infill patterning and creating this model design, you can actually now model how you're going to place your cells. That is by deciding printhead 1 and printhead 2. Say printhead 1 is only the bioink and printhead 2 is the cells that you want, and it would probably follow the motion that you require it to move. Say example, that zigzag sort of pattern where you want that cells to be embedded in. So you can actually modulate and design how you want your cells to be printed there. So then obviously the rest of the procedures come in. And you can imagine this being a stingray. So that is more about soft robotics in general. The applications are quite vast. Our idea is to make you understand the capability of getting to that extent and how we want to achieve that through, say, a technology like bioprinting. And now I'll take you to the next topic, which is organ on a chip. It's a very fascinating topic, honestly. Now, throughout the field of, say, pharmaceutical industry, drug discovery, drug delivery. So I'll just talk to you about what it actually means entirely, or rather the basics. So when you're talking about the interface between pharmaceutical, diagnostic, and 3D bioprinting, you have initial stages, right? So where you have drug discovery, and during the drug discovery, you take maybe a simple printed 3D model for initial validation of your drug, and then you go to a step where you have disease modeling. Disease modeling is going to be now creating more complex models, more multicellular models, and now you are going to make it more specific to the disease you want, and now you're going to test the efficacy of your drug. The next step or the next transition we go to would be toxicity screening, which is large replicable screening of toxicity for maybe key organs, say liver or cardiac tissue or anything is specific to that disease. So you're checking the effect of a drug on multiple parts of the body. And now there's something more interesting, which is precision medicine, and this is again coming into name and fame, and a lot of developments happening here. Because what if you could create a pill? What if you would create a drug for a person itself? Whatever drugs that are being put out in the market are actually generalized medicines, right? So they're just put out for symptoms. Now, what if you can create a drug which is specific to a person? So for that, we need certain type of platform. We need a stage where you can bring that about. So imagine that you have your devices, right? All of these devices that you have, your laptop, your computers, all of them started transitioning from larger size to something smaller. So they started going from your desktop PCs, your supercomputers, your laptops, and now you're going to like tablets and phones and something smaller. So as you're transitioning to that, we are also trying to create something more simple, right? Something more simple, something more understandable, and something more handy. The idea is to create lab on a chip, right? So we are going through this process of testing a medicine, testing anything as such, which is at a very large scale. What if you can concise all of that into one thing? What if you can simplify your problem, right? So that's where you have organ on a chip. So this is actually the reference to, again, biomimetic system, which uses a which uses an area, or uses a main application field, which is microfluidics. So microfluidics is actually somewhere you are uh, looking at a microscopic level of the fluidic nature, the fluid, how it flows through it. So example, you have a cell or you have any simple thing, you want to understand how the fluid interacts, how the fluid moves about that system, and how it creates the relevant physiological aspects that you want to create. So, the main thing about organ on a chip is that it refers to a physiological organ, right? So, and now this is built on a microfluidic chip, and this system itself is the whole lab. And that's where you're creating something as simple, and you're creating a tissue, or you would say, in a very generalized term, an organ in that specific chip. It's a microchip. So, you'll get a better reference here. You see this image here, you have yellow, blue, and then what comes out is green. So you're having basically input system and output system. This looks like a very generic model, and well, this is quite generic, but this gives us a good understanding of how you're looking at the microfluidic nature of whatever you're using as the inlet and what is the output, right? So when you're bringing that a system as a system to your cells, they are tiny fluidic channels that you're creating, and they're supposed to replicate either blood or air, right? Just as in our body. And now this enables flexibility, allows the chip to recreate the breathing motions and maybe the contractions. So you're going to create a chip which is going to act like a body, and it's also going to do some of the basic physiological functions. Say, example, breathing, right? So the movement of air in and outside, contraction, basically when there is a stimulation, how there is a relaxation and contraction behavior of maybe a muscle tissue. So these actually help us gain a better understanding of the effect of medicines on specific part of your body or even the entire human. So they use this as a example, or rather an application, in maybe diseases causing bacteria in foods, maybe any harmful materials that are available on any of the components, especially drug testing. So what we are trying to do here with organ on a chip is actually trying to replace animal testing and creating something more simple for humans. And they're trying to mass produce this so that you can have different types of organs, different types of tissues rather, there where you can test your drug conveniently, easily at maybe a tabletop, right? It's, you're just trying to create and evaluate the system where you're printing something, creating the physiological aspects required for that specific type of cell to live in, and then you're testing it or analyzing it to see how it's affecting the drug that you're trying to reproduce. Again, I'm going to show a video to make it much more easier for you to understand. This is a lung on a chip.
The lung on a chip is a microdevice that has the potential to replace animals for the testing of drugs and toxins. The device, which is lined by human cells, mimics the mechanical and chemical functions of a living, breathing lung. With every breath, air enters the lungs, filling and expanding microscopic air sacs. Oxygen is transferred across lung and capillary cells and into the bloodstream. This is also where aerosol drugs are absorbed and where infections and tumors form in the lung. The lung on a chip is crystal clear, flexible, and about the size of a small computer memory stick. But it contains tiny hollow channels created using microchip fabrication techniques. A porous, flexible membrane separates the two channels at the center of the device. The opposite sides of the membrane are lined by human lung and capillary blood vessel cells. This mimics the arrangement of lung and blood vessel cells in the air sac of the lung. Application of cyclic suction in side channels makes the entire flexible sheet and cells stretch and relax rhythmically, just like our lung cells do when we breathe. In the lung on a chip device, air flows over the top of the human lung cells, and a liquid medium containing human white blood cells flows below the capillary cell layer. To test how well the lung on a chip device replicates the natural responses of living lungs, we introduced bacteria into the air channel to mimic an infection. And we introduced white blood cells to the blood channel. We then saw the white blood cells migrate across the capillary cell layer, through the pores of the central membrane, and into the airspace where they engulfed the bacteria. Here's a video that
So, uh, like they showed in this video, they used lung, right? They try to mimic the whole action of breathing. So you have one side cells and the other side vacuum or air, and you're trying to see how it is transported across each membranes through obviously an artificial membrane put in. So you're also creating a rather 3D structure, a 3D platform for testing your testing your specific physiological organ that you're looking at. So this is the simple, rather a simple way of saying what organ on a chip is. Uh, so there are obviously manufacturing techniques. There are ways that people go about to create these chips. There is maybe micro machining or embossing, injection molding, laser ablation, and then 3D printing. Right. So 3D printing is in the general 3D printing where they use maybe glass or plastic material to create that chip. Well, you can avoid that. These conventional methods, right? If you remember, we are using cells. These are conventional methods, and we need to be considering whether the material that you're using is biocompatible, resorbable, and few other factors that you need to consider. So, if you're looking at something like these, and these are materials like say silicon, right? Silicon, which is PDMS, or maybe glass, or any other material that you're using, you are supposed to also check at the biocompatibility. You need to see that the cells you're putting in are actually alive, and that's a main challenge which people face. And that is where we are trying to get to better systems, better methods of creating. And 3D bioprinting is obviously one of those methods where you can conveniently create a space and environment for your cells to grow in. So there are examples wherein they have created maybe liver on a chip, lung on a chip we've already discussed. Then we have gut on a chip, and then we have maybe another organ being put. So you have different organs that you try to like create, or you can say spheroids or organoids, which are used to replicate that main function we are trying to do. Uh, so, considering all of these examples, I will just tell you what are the requirements. So, we do go from, say, lung or liver or heart or kidney and all of these organs, right? Uh, what if we could create human on a chip, right? That's very revolutionary, because what if you can do all your testing processes in just one system where you have lung for the absorption of drugs, heart for the contractibility and conduction, kidney for the excretion, maybe gut for absorption again, and metabolism and immune responses. So all of this are confined, and you've created one system which does all of these things for you. And we are close, you can say we are close, where people have created such working chips for advancing our drug development, advancing our physiological studies that we need to carry out. So when you are trying to bioprint it, right? So I talked about extrusion printing. Extrusion printing is actually where you're using a material which is, say, rather opaque, right? We are using something rather opaque, and here we require something which is more visible, something more clear. So you have materials and polymers, which is called PEGDA, right? They are used as materials to create these sort of structures with good resolution. Our resolution is the main idea, and we are trying to create resolution, mechanical strength, better visibility, and finer channels, because we are not only doing to create cells, we are also studying microfluidics. And microfluidics is quite a immense field where you need to go with a lot of iterations. There are a lot of designs you need to create, and there's a lot of intricacy you can do. It's not as simple as one line and two dots. It's a lot of it. People create very complex structures to see flow properties, to see how the cells respond to them. So we have one specific type of bioprinting which I have mentioned before, that is DLP bioprinting. So DLP bioprinting is where you use projected light to create slices of the image that you want, and these slices are now printed layer by layer, and as the light switches on and off, it starts printing and creating that watertight structure that you want. It consists of this PDMS, what a build platform, and rest of the other sections which combinedly make one tissue grow. So this is a device called Luminix which works on DLP. So it does a printing which is upside down. You go through this phase wherein you can just select what sort of light, what intensity of light you want. The material has been chosen. You can keep that material on that vat, which is a PDMS vat. And as the light projects, this goes on printing the structure that you require. So this up and down motion actually allows creating stacks, layers, and slices. So that's a general technique in creating organ on a chip kind of models where you can either create a chip, seed the cells, put the cells later, or you can just print it with the cells, avoiding any sort of loss of cell life. So we have products, say Incredible, BioX, BioX6, BioMDX, and Luminix, as you mentioned. We also have BioVia, one of the products I mentioned about. So this is for basically 3D protein engineering and biological design. And its capabilities include protein engineering, antibody modeling, simulations, X-ray analysis. So these are all simulation in silico sets that we use. Um, Following this, it's bioinformatics and cheminformatics capability of BioVia, which helps in maybe target selection, homology modeling, genomics, virtual screening, toxicity studies, etc. So just before I end the session, we have this quiz where you'll have to go to our LinkedIn or any other social media platforms. So the question is, which bioprinting technology is efficient in creating vascular channels? Vascular channel, I repeat, for tissue models. A is extrusion bioprinting, inkjet printing, DLP printing, fuse deposition modeling. So you can either scan the QR code which is on the screen, or you can just go on to LinkedIn and type in Altum Technologies, and you'll be able to answer. So this allows you to win a certain hamper or a gift voucher from our end, and this happens towards the end of the session. So thank you, and because of my fascination with biohybrid robotics, it has a potential of being fully autonomous, intelligent, and self-assembled. Thank you so much, and yeah, this is the end of the session.
Thank you, Aishwarya. That was really
Hi, yeah.
insightful.
Thank you.
And viewers, attendees, members of Biotechnica, thank you so much for attending it till the end. Now that we have achieved the end of day 2, and of course, we now have a surprise contest going on. Aishwarya, could you please make the PowerPoint full screen again and share back that QR code so that the students and the attendees could participate? Okay, I will again repeat, guys. So Altum Technologies got very much encouraged by all the responses they got in day 1, and they want to further, scale it up. And now we have a bio quiz for all of you. The data is given on the screen right now. Which bioprinting technology is efficient in creating vascular channel-like tissue models? So that's a question. There are 4 options. All you have to do is go to any of the social media pages of Altum Technologies. The QR code and the link is given over there. Please go there and answer the question, right? And of course, don't forget to follow them, because they are the leaders in bioprinting in our country, in the world, and they are going to give you gift hampers. So one random person will be chosen. And am I right, Aishwarya? One random person will be chosen.
The person who answers right, yeah. The person,
okay, so
yeah.
Okay, the person who answers right and the person who is first or something? First come, first serve? How do you?
First, and actually we have 5 other questions which will come, with the subsequent
in the future
sessions. Yes, so
right.
If they correctly answer all 5 questions, obviously the first 3 will will receive something.
Fantastic, fantastic. This is really encouraging. All right, so we have very less time, and throughout the session, what we've done is we have, picked up the questions which the attendees were asking. So I will quickly read out the questions for you, and you can start answering. In the meanwhile, people, we have very less time, so quickly we'll be picking 5 more questions from you. Just type Q and the question in the chat box, and we'll start picking it up. Okay. So let's start with the first question is from Mr. Nandu NS, and he asks, does the bioprinting application applicable to replace damaged internal organs in humans? Over to you.
Well, okay. So, bioprinted organs that you create, you can use it for maybe regeneration purpose, not entirely the whole structure, but you can say maybe part of it. Example, there is a study where they conducted to check the nerve model, right? So nerve is a simple structure which requires two connections. So you can create something like a nerve conduit to help in the regeneration. But when you're talking about organs, we are far from it.
Okay.
I
So I
hope
hope that
this
answers.
answers the question.
Yeah, answers the question, Mr. Nandu. We have next question from Anirban, and he asks how those bioprintable organ models are developed, how the blueprints are generated.
Okay, so say example, if you're talking about a general tissue or maybe a microfluidic, depends, right? If you're talking about general tissue, we would have to take some CT data, right? We have CAD data, CAD models that we used. So we use that as a main blueprint to create that design. With that design, we now convert it into slices, and then you create, layer by layer printing. So these slices convert into G code and create that structure. When it comes to microfluidics, it is actually quite complex because you have to go through quite a lot of studies within microfluidics itself as to see what is the best way your cell can get the most amount of nutrition, what is the best way your cells are more in contact with each other. So this is a kind of model you need to create and you need to design in the end to create that blueprint for your design.
All right. I hope that answers your question. Okay, Anirban. Next, we have a question from Rishikesh, and he asks how docking in homology modeling is used in 3D bioprinting.
Okay, so this is not exactly something which would come in 3D bioprinting. That whole concept is in drug discovery, drug delivery. So this is a precursor process. This is not something that will come later on. So that's just in helps you in drug discovery and drug delivery. In the next sessions, my colleague Divya is going to explain more about these, the whole process of BioV and how it works. So I hope then, if you attend, then you will get much more perspective on this. Yep.
All right. I hope that answers the question, Rishikesh. Moving ahead. Okay, we have a question from Mr. Robin. He asks, can we use this organ on a chip technique to understand unknown disease model? And could we identify the new diseases?
Okay, identifying a new disease is rather not the easiest. You can definitely create disease models. So the idea is to create disease models. So yes, this is the direct question to your direct answer to your question.
Mhm.
So you can definitely do that, but detecting a new disease is a whole different section.
Right. Okay, next question from Chagriti. What is the cost of organ on a chip?
Okay. The cost of organ on a chip, I don't know the exact cost, but the cost of creating it is something depending on the whole, the background. So this is definitely expensive, and this is less available in India for sure. We can just send in the links maybe so that you can understand better about it.
All right, that's a question from Raja Ram. Which bioinformatics software tools we are using for bioprinting?
Sorry, can you repeat that? I'm sorry, can you repeat that question?
It's on the screen. It's on the screen. You can check it out.
Hold on.
Which bioinformatics software tools we are using for bioprinting?
Okay, so here we don't. You can obviously go with BioVR. Bioinformatics software tool is a whole different thing. Like I've mentioned, Here we are just going with creating the model. So if you're talking with a bioinformatic tool, you can go with BioVia or any simulations to create, or rather talk about the protein designs or maybe the drug designs.
Right. So there was a question earlier in the webinar, and
Okay.
the question was by Dr. Hasna Abdul Salam, and she asked, "Is this technique useful in cancer treatment?"
Yes, if you're talking about bioprinting, yes, they have created models, cancer models, to actually do drug testing or drug analysis. So if not only bioprinting, organ on a chip itself is another pathway to drug cancer studies.
All right. So with this, we come to an end of our session. I know you have a lot of more questions, guys. So keep it on hold, and we'll meet in the next session where you can ask. Possibly Aishwarya and the team members at Alton, we will have to discuss maybe a separate session where we will just take up questions, because generally we are left with like 2 minutes, and then there'll be a lot of questions. I think that will do justice to all of them. All right. So guys, with me now, I have a small announcement to make, and now I have Mr. Abhishek Kalra, Associate Vice President, Altim Technologies Private Limited, with us, and I would like to invite him onto the screen. Hi, Abhishek. How are you?
Hi everyone, good evening. I'm very well. How are you?
And we are doing great. Thank you so much. So, guys, Abhishek was so excited seeing the response you guys gave to the first session and, of course, today's session. So he has personally joined in. He's a associate vice president of Altum Technologies, and he is involved in application engineering, product management, and pre-sales operations for digital manufacturing and digitization business unit. And Abhishek, a few words for our viewers today. Over to you.
Yes, first of all, I thank all of the attendees for attending both the sessions. I was saying that both the sessions put together, close to 7,000 plus people have joined the program, and I'm so glad to see so many questions coming up. Uh, Unfortunately, due to lack of time, we are not able to take all of them.
Right.
But as Shekhar said, we will organize a separate sessions where Aishwarya and one of our other colleague Divya will take up all the questions. Uh,
Right.
uh, we're going on through one of the biggest health crises in the world, and despite all the grim situation, uh, uh, what one very good thing has happened is that for the first time in the history of mankind, a medicine to an unknown disease has been developed in such a short period of time. And the earlier record was about 2.5 years. And this time, the scientists of our country and across the globe have managed to create a vaccine in less than 10 months. And none of this would have been possible without techniques like bioprinting and in silico modeling techniques with software such as BioVia. So the importance of all of this is only now that people are understanding.
Very
Everybody
true.
says that 3D printing is going to change the world and it's going to revolutionize everybody's lives. But if you ask common
Right.
people on the street, how is it going to do that? Nobody knows. So this is how 3D printing changes mine and your life. It allows us to create technologies, medical devices, medicines which can drastically reduce mortality rates and of a certain disease and drastically reduce the development time of new drugs. So once again, thank you so much for attending all of you to all of you, and I hope that the sessions are encouraging and maybe all of you and or some of you can start using these tools in your research. Thank you so much.
Thank you, Abhishek. So, guys, there you have had it, Mr. Abhishek, Associate Vice President at Altum, and of course, Aishwarya is still with us. Now, people, before I end this session, I really want to urge all of you to start looking at this particular field and the kind of advancement which is happening. Don't get left out. This is one such field which has tremendous implications in the future. And like Abhishek said, in such a small span of time, for the first time, they developed the vaccine, right? things are going to go fast forward from now on. This pandemic has opened the eyes of the world towards biosciences. And like I have always insisted, you have to stand at the boundaries of arts, science, and commerce, then only you can grow. You have to stand at the boundaries of IT, BT, and all such scientific tools. And bioprinting is one such tool. And Altim brings to us that tool into India. Now, people, if you want to use Altim's bioprinting technology in your research, you know where to go. LinkedIn page of Altim, or just go to Altim Technologies website, contact them, and they will certainly be there to help you, guide you, and accelerate your research results. Right now is the time for feedback form. I can see a lot of people asking for that, so we won't disappoint you. Go ahead. So our team will post the feedback form right now. Even I will post it personally in the comment box. And I would like to personally thank all those people. I would like to personally thank all those people who joined this seminar, this webinar series on my personal request. I sent a personal mail this evening to all of you, and I know most of you have joined using that link. Thank you so much, and please connect with me on LinkedIn. Okay, you can just go to LinkedIn, write Shekhar Suman Biotechnica, and you can connect with me. You can ask questions to me, and I would make sure that personally I am able to answer most of the questions, right? And with this, we come to an end of our session. Aishwarya, once again, heartfelt thanks to you. You are an amazing speaker, a very knowledgeable person, and I must say you are truly an asset to Altum. Thank you so much for joining in today evening, and thank you, Abhishek, once again. Guys, with this, we come to an end. I know you have questions. I know you may wish to ask more questions. So definitely we're going to have more sessions like these, right? But our speakers need encouragement. They have just conducted 2 sessions. They need to last for 4 more sessions. So don't forget, share it on LinkedIn, Facebook, Twitter, wherever possible, WhatsApp. Let people know that this is something great happening. Invite all of them together. The more people view, it will encourage more companies like Altum to come on board and support all of you, right? Isn't that amazing? So what should we do? Please share. Sharing is caring for our speakers, for all of the people who will be watching it in the future. Thank you so much. Good evening, good night, and I'll see you in the next session.